Today's diving helmets are produced primarily for history buffs and divers performing underwater work, such as welding the submerged parts of bridges. Unlike a scuba tank, which carries a limited amount of oxygen, a helmet connects to an air pump at the surface, providing an unlimited air supply. A diving helmet is completely watertight, so the diver doesn't need a mouthpiece to breathe and can speak to people at the surface via a built-in transceiver. This helmet is the design the U.S. Navy used from 1916 until 1984. At the factory, they make the helmet's head portion, called the bonnet, from a copper sheet about 1.5 millimeters thick that's been spun on a lathe into a dome. They buff it smooth, then using a template, mark where to cut openings for the various components. It takes a good month and a half for the factory to machine all those components and assemble the helmet. With a hammer and punch, they dimple the copper at the marked spots. This will give the saw a foothold on the otherwise slippery surface. Then they apply cutting oil to prevent the saw from overheating as it bores through the metal. The first cut is a 6-inch wide hole at the front for the bonnet's hinged faceplate. They saw 8 openings for the bonnet's other components, including 3 windows. Next, with tin and lead solder, they fuse a threaded neck ring to the bottom edge. This ring attaches the bonnet to the helmet's breastplate, which bolts to the collar of the diver's dry suit. Then they solder a base to the faceplate opening. Like all the helmet's components, it's made of red brass, which is more durable than standard brass due to its higher copper content. Next, through a template, they drill holes into a banana-shaped brass exhaust tube. It enables the diver's exhaled air to exit the helmet. They solder the exhaust to the bonnet, positioning the non-perforated end over a hole near the diver's mouth and the perforated end at the rear. This directs air bubbles behind the diver, so as not to obstruct the view. Then they solder on the remaining components, including 3 window bases. Just as one does when installing a window in a building, they apply glazing to the faceplate and window bases to seal the 3-inch thick acrylic pane against leaks. For underwater safety, they screw a brass guard to the base. This prevents the pane from popping out should too much air pressure build up inside the helmet. Now they install the transceiver and feed its wires through a brass elbow, which will ultimately attach to a communications cable running to the surface. With the bonnet complete, it's time to shape the helmet's breastplate. They lay a copper sheet onto a breastplate-shaped mandrel, clamp on a breastplate-shaped form, heat the copper with a torch to make it malleable. Then, with a wooden mallet soaked in brine to keep it from splitting, pound the copper for about 45 minutes until it assumes the shape. Then they chisel out the neck opening. Once the copper has cooled, they transfer the breastplate to a form and begin reinforcing the bottom with a brass strap. After clamping the strap in position, they hammer the copper around and over its outer edge. Then they remove the clamps and solder the copper to the strap. Once the soldering's done, they grind the surface smooth and drill 12 holes into the strap for the custom-made bolts that connect the helmet to the collar of the diver's dry suit. Then, after flipping the breastplate upside down, they wrap solder around the bolts, drop them in the holes, and melt the solder to lock them in. They polish the metal and solder on the last breastplate components, a threaded neck ring for connecting the bonnet, and, at the front, a pair of brass eyes for lashing the air and communication hoses off to the side, so they won't get in the diver's way underwater. A reef aquarium takes underwater exploration to a whole new sea level. It's a mini coral reef system recreated in a glass tank. Installed in a home or business, a reef aquarium allows people to see life on the bottom of the sea without donning a wetsuit and a snorkel. A reef aquarium is a living, breathing, and growing ecosystem. Along with tropical fish, it has spectacular coral and more low-profile organisms like crab, shrimp, and tiny aquatic creatures. All these organisms act as a biological filtration system for the water in the tank. They supplement the biological filtration system with mechanical and chemical ones. The assembler starts with a pump that recirculates the water. He installs it in a tank under the display tank. This tank is known as the sump. He places the protein skimmer in the sump beside the pump. This unit injects air bubbles into the water to remove organic compounds before they decompose and become waste. He adds a UV sterilizer. It has a high-intensity light that will be activated when needed to kill free-floating bacteria, parasites, and algae. Next, he introduces the media reactor. This cylindrical device contains both activated carbon and an aluminum-based media. These materials will absorb fish waste byproducts, thereby removing them from the water. With the mechanical and chemical filters in place, he now moves on to the display tank. He spreads real ocean sand on the bottom. This sand will be a habitat for some of the bacteria and other organisms that will aid in the biological filtering process. He selects rocks from a supply tank and transfers them to the aquarium. The rocks are home to numerous algae, bacteria, and small invertebrates. This makes them the central part of the aquarium's biological filtering system. He now prepares the ocean potion, adding synthetic sea salt to water. A pump circulates the water as the salt dissolves over a period of 24 hours. He presses a switch, and the premix of water and salt flows into the tank. This water now needs to mature. It will take weeks for tiny aquatic creatures to begin to thrive in this water. During this time, the filtering equipment in the pump below helps keep it clean. The protein skimmer foams up as the water constantly circulates through it. After about 3 weeks, there are enough microorganisms in the water. It's ready for coral and fish. These corals have been grown on an ocean farm and kept in this holding tank for this very moment. Each coral is composed of tiny, fragile animals called coral polyps. They are essentially little colonies. As the aquarium technician makes his selections, he considers how the coral will adapt to light and water motion, and how compatible the corals will be with one another. Some corals are very territorial and may release toxins when they come into contact with other corals. He leaves a lot of space between the corals to give them room to grow. Allowed to thrive, some will triple in size. He now introduces fish. Clearly, this aquarium has all the comforts of home. He installs a lighting system overhead that mimics ocean light at different times of day: sunrise, daytime, and sunset. For the creatures in this reef aquarium, light is a source of energy. With the reef aquarium now complete, the monitoring begins. He'll test the water chemistry regularly to ensure the right environment is being achieved. The activity of the fish and coral will be under observation to confirm this mini reef system is becoming a thriving marine community. Only then will this reef aquarium be ready to go public. So much more than a fishbowl, the reef aquarium brings the wonders of the ocean to the surface. Oceanographic buoys enable scientists to study the sea, help meteorologists predict weather, and rescue teams better define a search area. The top part of the buoy houses instrumentation that tracks temperature, surface currents, and other conditions. Its antenna transmits the data via satellite to a base station. This model has a ball-shaped surface float with a tether cable connecting a long fabric tube called a drogue. The drogue detects water movement several yards below the surface. The component that connects the surface float to the cable is called the stress relief. The factory makes this part in a mold, casting 10 at a time. Workers inject liquid urethane into the mold cavities. It's the same material from which inline skate wheels are made. After 3 hours, they extract the castings, which then cure for a full week. The surface float contains a barometer sensor that collects air pressure data, as well as a temperature sensor and a locating system. A 13.5-volt battery pack powers all these instruments. Workers build it by arranging 36 standard D-cell batteries. Using nickel strips, they make pairs, linking a negative end to a positive end. Then they spot weld the strips, creating circuit pathways along which electricity will flow. Next, they immobilize the batteries by filling the spaces between them with hot glue. Then they weld the final connections and solder on the leads that'll connect the battery pack to the instrumentation. Now they apply special insulating paper to prevent the battery pack from shorting, should it come into contact with a metal object. A wide band of electrical tape safely seals this 13-pound battery pack. The nylon polypropylene drogue is too lightweight to hang vertically in the water, so it needs something to weigh it down. That something is a heavy plastic hoop. They make the hoop by blowing sand into a plastic garden hose. The sand makes it heavy. After capping the hose, they insert it in a pocket at the bottom of the drogue. So now the drogue, all 26 feet of it, will dangle straight down into the water. Now for that stress relief they molded earlier on. It attaches underneath the bottom half of the surface float. Inside the bottom half, they install the battery pack, then a control board, a transmitter, and an antenna. The surface float is made of ABS plastic. The top surface coated for UV protection, because it will be exposed to direct sunlight. They attach one end of the tether cable to the stress relief and the other end to the drogue. They reinforce the connection with epoxy. This type of buoy is designed to monitor only the top yard of water, so it doesn't have a long vertical drogue like the other one. What it does have is a parachute, because it's designed to be dropped by aircraft in a search and rescue operation to mark the location of an incident. As the demonstration shows, the buoy opens on impact. All the components are spring-loaded, floats made of foam, drogues around a central cylinder housing the instrumentation, and on top, an antenna. The buoy packaging is water-soluble and biodegradable, so over time it simply disintegrates. No need to retrieve them. A sail is essentially a vertical wing that provides forward thrust and lift to propel a boat over water. It's impossible to know who came up with the concept because boats with sails have been plying waterways for thousands of years. But there's no doubt that when it comes to their design and construction, today's sails have come a long way. For thousands of years, sails were square, but in the 3rd century, triangular sails appeared on the Mediterranean. The shape enabled boats to sail into the wind as well as with it. Modern racing sails are made of laminated synthetics. They start with a plastic membrane. Rollers apply a hot liquid adhesive to one side in measured amounts because even a couple of extra grams would weigh down the sail. They press a scrim onto the hot adhesive. It's a super-strength synthetic called aramid, which will keep the sail from tearing. Then it's over to a computerized laser that cuts patterns out of the scrim-reinforced plastic. A worker rolls up each panel to transport it to the next work table. Here they tape 10 to 20 of the panels together using heavy-duty PET plastic with an acrylic adhesive. Now, hundreds of small jacks stretch aluminized plastic around a framework, pulling material into a curved aerodynamic shape. This mold will be used to shape the sail. The team stretches clear plastic film over it. Then they drape the joined panels over top. They use ropes and clamps to pull it to the contours of the mold. And now they're ready for some super tough synthetics, aramid and carbon fiber yarns. The yarns have been coated with adhesive, so they'll stick to the plastic film. A robot rolls the yarns onto the film, while a worker follows in a harness overhead to keep an eye on the job. The robot applies the yarns in a pattern plotted by an engineer to anticipate the wind load on this sail. The robot now switches from a vertical path to a horizontal one, applying yarns in a transverse pattern. The team installs a long, narrow pocket over that section. A batten will later be inserted in this pocket to control the sail's shape. They pull another layer of scrim-enhanced plastic on top, and now all the layers of this sailcloth are in place. A worker hovers overhead to inspect the surface for defects. They now seal the assembled sail in a vacuum bag and attach hoses. The hoses suck out the air, pressing the layers of the sail together. Now the robot applies heat to the sail. It activates the adhesives in the plastics to laminate the layers together. And it also sets the three-dimensional shape of the sail. A worker inspects the job with a magnifying glass. Then it's over to a revolving sewing turret. As the sewing machine turns, it pulls the sail forward, allowing the operator to stitch hems, grommets, and reinforcements onto it. They apply the corporate logo. Next, a worker walks the length of this enormous sail to inspect it. No imperfections will be tolerated. After all, this is a big-ticket item. Large racing sails can retail for hundreds of thousands of dollars. Sophisticated engineering and high-tech materials have produced a racing sail that's lightweight, yet incredibly strong. There may be rough water ahead, but with technology on their side, This crew should be able to sail right through it. When luring fish to a hole in a frozen lake, it helps to take a crafty approach. It's a handcrafted piece of folk art, and it's also a cunning piece of work. Often brightly colored with bold patterns, the decoy attracts the attention of fish, an attraction that will likely prove fatal. Native North Americans were the first to use decoys to catch fish in the winter. European settlers followed their example. And centuries later, decoy artists carry on this tradition of trickery. At this workshop, the decoy starts with a plank of white cedar. It's a wood with dense fibers, so it won't expand when wet. He draws a basic fish shape on the wood freestyle. This one is to resemble a herring. He carves out the shape with a bandsaw, producing the blank, which can now be transformed into a fish decoy. He cuts a narrow slot for attaching a metal tail fin. He draws a center line around the decoy blank. This serves as a reference point as he now tapers the edges with a sharp knife. If he cuts too deep, he could spoil the carving, so he whittles carefully, removing just a bit of wood with each stroke of the knife. The goal is to round the sharp edges and soften the profile, without cutting too deep and gouging the wood. He sands the entire surface of the decoy until it's perfectly smooth. Sanding also opens up the pores of the wood so paint will adhere. He carves a mouth, and then cuts slits for 2 sets of side fins. Using a power carver, he now bores into the wood to create fish eye sockets on both sides. He takes an equal amount of 2 epoxy clay components and kneads the 2 together. This activates the ingredients, turning it into a putty-like adhesive. He presses some of the adhesive into each of the decoy's eye sockets. He presses the glass eyes into the epoxy-filled sockets. Next, he cuts 6 fish fins from a sheet of aluminum, creating 1 dorsal fin, 2 sets of side fins, and a large tail fin. He inserts the fins into slots in the carving. He then drills holes in the wood on each side. He presses nails into those holes using pliers. This secures the tail fin. The fins on decoys are larger than on live fish to enable them to swim well when weighted. He now carves a pocket for the lead weight in the decoy belly. He inserts the front side fins so that they protrude slightly into the freshly carved pocket. He scoops up molten lead and pours it into the pocket. As the lead solidifies, it weights the decoy so it will sink, and it also secures the 2 side fins. He applies epoxy to the lead, sealing it so it won't be exposed to the water. He coats the entire decoy with lacquer. This seals the wood against water, which would have caused the wood to swell, cracking the final finish. Once the lacquer dries and the paint has been scraped off the eyes, the decoy is ready to take the plunge. He tests it to confirm that it sinks and that it sits level underwater and swims. Sometimes more lead needs to be added, but in this case, the decoy performs fine underwater. He marks a spot for a screw eye for threading fishing line, and then twists the screw eye into that spot. He paints the herring decoy a vibrant red, a color that isn't scientifically accurate, but one that should tantalize real fish. Decoys are often exact copies of fish. They're designed to simply pique their curiosity. Since fish are attracted by colors and shapes they don't normally see, decoy artists can be as creative as they like. Considered a form of folk art, Fish decoys are often entered into competitions. But of course, when it comes to their underwater allure, the real judges are the fish.
Everybody knows about drones that fly, but there's also a new class of autonomous vehicles that can travel the ocean. Some dive and some sail, but very few can do both. An ocean drone transformer shifts from sailboat to submarine by rearranging its shape and completely altering its mode of operation. This is an autonomous, unmanned, underwater and surface vehicle. It's an ocean-going, information-gathering robot, capable of propelling itself both over and under the waves, using nothing but wind and solar power. To create the vehicle's hull, technicians unroll sheets of fiberglass over a mold, which has been machined from a block of styrofoam. They cut the fabric to fit. Fiberglass is the preferred material, thanks to its extraordinary durability, which will allow the craft to spend months at a time at sea. Additionally, fiberglass won't interfere with the vessel's electronic signals. They carefully tape the material to the mold. This yellow material will allow liquid resin to flow easily. They unroll a gray ribbon, which will also help direct the flow of resin. They make an incision in the middle of the ribbon for a nozzle, which will be the entry point for the resin. They tape on a layer of plastic, which will allow them to vacuum seal the assembly. A shut-off valve helps control the flow of resin. The technicians pour resin into a container. They vacuum seal the assembly, and as the resin infuses the flow media, it displaces the vacuum until it has completely saturated the fiberglass material. The resin cures for 12 hours. The mold splits open at the bottom, so technicians can release the hull assembly. A technician paints the vehicle's keel, which is made of marine-grade aluminum. The torpedo-shaped keel bulb is made of lead. Electric cables run through a hole drilled lengthwise down the center of the keel. The interior structure of the vehicle starts out as a flat material made from a combination of fiberglass and epoxy, which they form into large sheets using intense heat and pressure. Water jet technology then precision cuts the 3.2 millimeter sheets into the required shapes. Technicians assemble the shapes into a structure that will support the hull while housing the vehicle's equipment. In-house technicians build the multiple circuit boards that make up the Central Processing Unit, or CPU. Each board controls a separate element of the vehicle, such as the sensors, the wing, or the communications system. Electronics and water are not a good combination, so the manufacturer designed a watertight acrylic tube to hold all 10 of the circuit boards that make up the CPU. Specialized cable connectors ensure no water gets in through the cover plate. Once the enclosure is sealed, technicians vacuum out flammable oxygen and pump in non-flammable gases to protect the CPU. A technician prepares the battery, which is an off-the-shelf lithium-ion unit. They 3D print a battery housing out of ABS and infuse it with epoxy to ensure that it's completely watertight. A technician installs the battery in its designated spot and hooks it up. Solar panels on the vehicle's surface will recharge the batteries. A hose will allow the CPU to transfer water from one ballast tank to another to control the boat's up and down motion or pitch. The vehicle's tails are actually housings for backup communications antenna. In stealth mode, the vehicle can sit below the water surface with only its tails above the waves. To ease transport, the tails are designed to pivot out of the way. The technicians have now installed the ballast tanks, emergency backup systems, and all other internal components. Now it just needs a cover. The solar-paneled cover slots around the wing. Designed to fold down and tuck into the body of the vehicle, The rigid wing multitasks as the primary antenna and the sail, which propels the vehicle when it's above water. Users can pre-program a mission and change it anytime via satellite or Wi-Fi.